this is our 550 project, and in this project we will use this 4-degree of freedom manipulator to autonomously retrieve some object using its magnetic and effector. And to do this, we also have a camera on the top. It will locate all the cups and annulus. And specifically, we will go through a camera calibration and template matching to locate every object, and then our autonomous path planning.
So first, we need to calibrate our overhead camera. This is so that we can translate the pixel coordinates that the camera gives us into workspace coordinates for the robot. And this is useful especially for finding the obstacles in the scene. So the way that we're going to do this is we will have 4 separate calibration points, which are on these corners. And we need at least 3 points in order to perform the linear regression. But 4 points will give us a more accurate transformation matrix between the pixel space of the camera and our workspace coordinate. And now we will demonstrate the calibration of the camera. So first you can see that the coordinate frame of the camera is off-center. We want it to be on the center of the robot. So now we will click on the 4 calibration points. And now you can see that we have a graphic.
Okay. So the second part we want to implement is called template match. Template match is a method that we have implemented to identify the locations of the obstacles on the board from the camera. This is important to our project because later when we conduct the path planning for the robotics arm, we will need to know the locations of all these curbs and annulus in order to reach the location that we expect it to be without colliding with anything. So the second part we want to demonstrate is called template match. Template match is a method that we have implemented to identify the locations of the cups and the annulus from the camera. So by selecting a template image on the board, so say this is a cup template, and then we compare it with every single pixels on the camera view so that we can identify the locations of the cup. And once we find the cup, the GUI will give us like a red circles on top of the obstacles we have found. And then we can select another template for the annulus, which is the location where the goal is. And then we can find the annulus by clicking on Find Torus. And once it identifies all these torus, it will add green circles on top of it. This is important to our project because later the robotics will need the locations of all these obstacles and annulus in order to avoid the obstacles and then reach the goals in the annulus.
Okay, so now we're going to begin the path planning. So first we have the potential field planner, which assigns a scalar value to every point in the workspace. And what we're going to do is going to take the gradient of that potential and descend along this gradient to the goal position. And in addition, there's a repulsive potential from each of the obstacles so that we can avoid collisions. So now you can see the robot approach the goal, and as it gets near to the goal, there's a little bit of shaking due to the repulsive potential, and then it returns the ball back to the start. And then it will continue on to each of the goal positions.
So the second path plan method we want to implement is called PRM. PRM stands for probabilistic road map method. So in this method, we have constructed a well-planned map for the robotics arm to follow. In this algorithm, it will randomly generate all different kinds of configurations for this robotics arm all above the board, and we check each configuration against all these obstacles that we have identified from the template match, so to make sure that each configuration is free from collision. So by constructing this kind of map, the robotics arm will be free to move from one position to another position without concerning about colliding with obstacles. Comparing to potential field, PRM is better for global path planning, while potential field itself is better for local path planning.